and when Republicans are sensitive. So he was a small cell. Because ours is here. I thought this is like when I read, I said this in April. I'm scared that there's no way that I set this high at the same time as I set this to read so that the delay here to come back and add only between two. Because I don't know, I heard this even from the big plot. But on the next shot cycle my name is no, I tied it to my space. That reinstated I said this guy's great. And I said that guy's actually I want to make said yeah, I'm the worst thing. Yeah. But the plot doesn't count. That's why I changed state. They're smart. Especially with all the issues. That's
It was more tedious than like the 140 was at least it's like conceptually that shit. Like this was
type it in.
yeah. It just took like it didn't take very long. Like it was the most tedious. Like I couldn't make myself do it. I kept watching anime episodes in between because I couldn't like go through it like in one go. In reality, it took me like probably like 2 hours, but like total time spent on like just the math was probably like 5 hours. I don't have the CD, but I have the entire series, but you can probably get better quality. Like all I have is I have a shitload of Hong Kong subs, which is just like they switch it. Do you know anything about the series? Okay, you wanna watch it? Huh? Okay. Yeah, I might want to download better quality because I haven't actually seen. I've seen parts and stuff with the whole series, but I haven't bothered to watch it because like the quality I have is so bad. Like these switch two of the characters' names, two of the main characters' names. You switch them, and like the English is not understandable. Like you can't understand what they're saying. It's so bad.
I thought like especially in the movies you watch them with subtitles.
No, only up to a point. Up to a point, it was fine. Beyond that, it became too weird. Still, it's pretty shitty quality. Like now, you can probably get everything on DVD, like DVD quality, really good stuff. I didn't even have the compilation side.
I signed up for one of the Canadian episodes.
The password is obsolete.
I just signed up because in case
What?
they have access to the password.
That's smart.
And it drops after like a week.
That's smart.
Yeah. Like first week you go to the cartoon place, you try to download something, they check your account, and once you have access they drop the password.
That's smart.
And then you can print unlimited printing using the service. Oh, right. You have that print. You drop it and like once you restart it's the same quality every time.
Probably good. I had to try it out first. What are you taking? You're taking
No, I
340?
don't know. I won't get another one.
What are you taking? 340 or 130?
240, 130. And the E190.
Still quite a bit.
Are you taking E190?
I don't haven't even taken it.
Oh.
I don't know what I'm gonna do next semester. I think I might just do. Actually, I might actually be cool. I might just be like, I might just take 125.
What class?
Well, I mean, like as far as the CCs go, social physics.
Oh, physics is good.
I don't think so. History, not. I'm probably gonna take relative and cultural.
What's relative?
161. It's processed with astronomy.
You're combining writing and reading. That's funny you say writing. I was like, yeah, now that I heard that, you are writing things.
Hey Jack, have you ever met any geniuses in this? Have you ever met any geniuses in this?
Yeah, yeah.
Yeah?
Yeah, it's like, wow. It's like, I was like, wow, this is like something out of nature. Like, this is really smart. I'll try introducing you guys. Like, hi everybody, my name's gonna be Josh. I'll be substituting. That's what Josh said today.
So who can tell me what feedback is? Because I don't know. Who can tell me?
No, I already sent it to you.
Jack! It's terrible. Jack, do you understand this stuff?
Do something useful. Huh?
Do you understand this stuff?
A little bit now. I'm getting better at it. I rewatched some old lectures.
Explain it to me then. That's useful.
Okay,
It's like, no,
so
that's not useful. Get away from me.
you have a game and feedback. You have those equations, and then you have that set of equations on the first page as feedback. The AF. UCF coordinates. Yeah, that's fine.
How do you calculate R out?
R out. You take you you have to calculate R out. You break the feedback in a place where you break. You have to be able to break the feedback, and then you calculate the R out
Right. Well, okay. So
here,
there's.
and then you divide or multiply by what
Were you guys
must be,
keeping him in
depending on
comp
what
sci or
kind
something?
of
Were you guys keeping him in comp sci? Oh, because he came in the grade before.
that right? It's pretty scary up here. I ask those people all the questions.
Oh boy. Oh boy.
Oh boy, I make sure you're sleeping. I can really tell. All right. Okay, let's go. It's all right. We were in office hours over there and just didn't watch the time, so I'm sorry I've been late. Okay, have the. This is a little bit used up. Okay, I guess we're going. Going, coming. Are we going? Okay. This has seemed. So the. Okay, the. Down here on the. Hello. Okay. Should be on here. I don't have my. Okay, so the there we go. Okay, the this is the histogram of the FOMs, and what all is scribbling here is we're trying to figure out exactly how I'm going to grade it yet. But there's 25 points that I have to distribute somehow or other, but I haven't quite figured that out yet. So I'll work on that, and hopefully I'll be able to turn these back by Wednesday. The this is up to, I guess the highest one was 5.8 gigahertz. Okay, and this is on gigahertz scale. So this is 1 gigahertz, 2 gigahertz, 3, 4. Each one of these corresponds, we think, to one person or one group or maybe two groups. I'm not sure, right? So, but anyway, so 1 gigahertz, and then there's a big bunch of people down here in the region below 200 megahertz. You know, like group 10 of them. So that's the FOM. So I'll hopefully, I haven't quite figured out how we'll score. I mean, you know, divvy up to 25 points across this thing. Be more for people at this end and less for people in this end. I'll tell you that right now. But besides that, I'm not quite sure yet. Okay. Let's see. Homework. I also apologize, being late today, and for not doing the material that you needed for your homework last Wednesday. I didn't realize that I had to get through some more material. So I'm going to delay the homework till next Monday. Okay. What? When will the late homework due? I guess by the Wednesday following that Monday. Okay, right. Okay. All right. So, sorry about that. I didn't realize I was behind. Okay. What I'm going to do today is what you need for your homework. All right. And so yes.
When's the project 3 coming out?
Project will come out Wednesday.
Is it individual or?
Pardon?
Is it individual? Or?
It'll be groups, so you keep the same group, you know, if you want. So keep the same pairs, and it'll come out Wednesday. And it'll be due the last day of classes. Like I could send in the notes or the yeah. Is there a class Wednesday? Yes, I think so. I'm gonna be here, I think. Yeah, I'm leaving right afterwards, but yes. Okay, here we go. Okay, so this is the rest of what makes designing the whole op-amp circuit interesting. Okay, all right. What we've been talking about is frequency response. We've been worrying about stability. Now here's another set of specifications that you have to deal with, and the homework begins to address this to some extent. Okay, if we take an op-amp, and let's just take unity gain feedback. So this is kind of the voltage follower mode, right? What kind of feedback is this? Who can tell me? Series shunt. Series shunt, right? We're attached right to the output. It comes back in series with the input, and we have a V error right here. So this is series shunt feedback. Exactly right. Okay. So for this series shunt feedback network, if we put a step into Vin, so now we're worried about a time domain response. Okay. So this is a function of time here that I'm talking about. Okay. What will happen on the output is this is the input, this is Vin. This is what's going to happen on Vout. what's going to happen on V out is there'll be two regimes of operation, and I'll expand this in a second. The first will be a period of time where the output just, they call it slews. And basically what the output's doing, it's in a linear ramp mode. So it actually is not a function of the input signal. And during this period, if I put a smaller signal in, it'll go right up the same curve and then start going into a small signal settling response. So it's a non-linear response, and it's very nasty for if you're trying to get a high-performance audio system, for example, because this thing here, it's a non-linear response. It's spraying out all sorts of frequencies and stuff that are not, what you're putting in. So this is creating new outputs. It'll sound very bad to your ear. So this non-linear response is part one that you're going to have to deal with. We'll talk about where that comes from today. Then after you finish that, you go into a small signal settling. So this is a large signal effect here. What's happening here is transistors in the circuit, your op amp, are going into saturation, or going into cutoff. So the circuit's really got into it's not a small signal model anymore, okay? After it comes out of that period mode, in other words, what happens is when you first put the signal in, you have a huge input. This output hasn't changed yet. So if you put in 1 volt here, you've got 1 volt across your input. If you think about this input being an input differential pair, you put a volt across that input, what happens to it? Well, that pair just goes into one side or the other, cuts off, okay? And so that's why you have why it causes the slew rate problem. Now, after the slewing goes on for a while and the output begins to sort of try to come up to equal to the input voltage, in other words, V air gets set to be smaller and smaller, then finally that op amp turns into a linear circuit again, okay? Then when you're in a linear regime, in other words, no transistors cut off anymore, then you begin to go into this small signal settling period. And this is what we've been analyzing up to now, actually. So this region down here, this large signal slew rate period, is something we haven't analyzed at all before. The small signal settling is what which we have been analyzing. Now, what does it do in there? It can ring for a while. In fact, if it keeps ringing forever, what's that? It's instability, okay? In other words, so as you make the circuit more and more stable, what will happen is this ringing will get less and less, okay? So let me show you what that looks like. So now I'm talking about this little region right at the top. We've gone through the slew rate period. Now we're in the small signal settling period, okay? And what's happening is if we have a very large phase margin, this is phase margin, we'll get a nice slow response. The circuit's very, very stable. As we reduce the phase margin, make it smaller and smaller, what will happen is the circuit will respond faster, right? But it'll begin to ring more. Now the question is, we will give you a specification on the project, and this will be the primary specification on the project. This thing will settle out to some value. So let's say it settles out to, V out final, okay? We can talk about what that value is. But what we'll do is we'll put some error bars on this thing. We'll say the answer is once the output stops ringing, okay, sort of this ripple thing, to within, let's say, plus or minus, I'm not sure, we'll have to decide, probably like 0.1% of what the final value should be, okay, V out should be, then we say that the circuit has settled, okay? So there's a rise time, there's a rise time, a settling time, okay, that we have to deal with, a rise settling time, rise time settling, right? Starting from right here, so let's call this t equals 0, to when it finally settles out. So let me just redraw that. This is going to go messy here. So we put this input step in, and the output will then go ramp. It'll slew for a while, then it'll start settling, and we'll look for when the output gets within, plus or minus, some number like 0.1% of this V out final value, okay? Now, in actual fact, we got another thing we have to worry about here. Okay, so what is V out final? Can we specify that? And we'll probably do that as well. So what is V out final equal to? This is after all the small signal settling things have happened. So for this circuit, it's equal to 1 over F times T over 1 plus T. All right? So what is T now equal to? Well, T, okay, is equal to A0 times F. Now this is the DC response, because after the thing settles out, you're really talking about the DC response, right? Okay, yeah.
Shouldn't be the V out final equal to 1 over T 1 plus T times the V in.
So say again now, sorry. Say it again. Right. All right. It should be. Oh, that you wanted this here, though. Okay, right. I'm sorry. Okay, yeah. Right, that was actually not. Okay. Anyway, right. Back to work here. Okay, so A0 times F is what this T0 is. It's really just T0. It's a small settling we have to deal with. And the F is equal to 1, so for F equal to 1, this degenerates to V out over V in will be equal to 1, okay, times A0 over 1 plus A0, okay. And if we want the final answer to be within 0.1%, what does that tell us? A0 is probably going to be much, much greater than 1. Okay, so if we take this, divide by A0, we get 1 over 1 plus 1 over A0, okay, divided by top and bottom by A0. And this we can sort of do a little Taylor expansion on, right? So we do a 1 minus 1 over A0 in higher order terms. So you can sort of see that the DC gain gives us a specification, how we specify or control how accurate our final response is. Okay, so if I say I want the answer to within 0.1%, what does that say A0 has to be? At least what? See what's going on here? So V out over V in is equal to, after this little expansion, is 1 minus 1 over A0. Okay, plus dot, 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 okay? It has to be 1,000, right? I mean, that means we'd like the answer, we'd like V out to be exactly equal to V in. That's ideally for this kind of feedback. But we're going to get an error because of this T over 1 plus T, or A0 over 1 plus A0 for F equal to 1. So that means that we're going to have to, if we have our A0 equal to 1,000, that means this will be 1 minus 0.001 or 0.999, which is actually a 0.1% error. Okay? Well, that's not going to quite do it either, right? Because what's going to happen then is this output's going to come up, it'll settle the 0.999, all right? But that means we're right at the very bottom edge of our bound, okay? If we say that we'd like the output V out exactly equal to V in, gain of 1, then we're going to, if we set ourselves with a gain of 1,000, we're right at the very small edge, and so any rippling at all will probably bring us out of our error bars here that we have to deal with. So probably have more than a gain of 1,000. Now, of course, as you have more than a gain of 1,000, what's that do to your bandwidth? Bandwidth starts going down, right? So you get less bandwidth. So here's another trade-off you're going to have to make. You're going to have to decide how much gain you have, okay, DC gain, at least 1,000 if we use 0.1%, and then, but you don't want to have a whole lot of extra gain because then that's going to make your bandwidth less. What we'll specify is this time that you get down within, where your output settles down to within this plus or minus 0.1% period. Okay?
So that would be the FOM that's fine.
Yeah.
How does bandwidth play into that?
How does bandwidth play into it? I'll do some more stuff on this in a second. You'll see. Okay. But you can conceptually you kind of know that more bandwidth I mean, more gain, less bandwidth, right? And I'll get more explicitly how that works, but because you're kind of fundamentally set by that gain bandwidth product issue.
Why would you want bigger bandwidth? Bigger bandwidth?
Because you want to settle fast, right? Because you want to settle. I mean, if I put a signal in, I want this thing to settle out. I don't want to have spurious responses from the amplifier still occurring, right? I'd like to have a nice settled time. We'll talk about switch capacitor filters and A to D converters and stuff like that next week, or and what you will see in there that quite often what we are worried about is this long-term settling and how fast we can get there. It turns out that's the way we use these circuits. We quite often put a step into it, get the response, put another step into it, get the response. That's how we do these circuits. So I'll show you that coming up. Okay, so you got the picture? So a new thing to worry about now. So we have to worry about the settling time, which is composed of a slew rate period and a small signal settling period, as well as composed of this long-term settling, which is controlled by your DC response. Okay? Okie doke. Let's go back and see where slew rate comes from. Okay? All right, good old Miller op amp. Right? Here's our differential pair, our input. Here's, let's say, our common source gain stage with the coupling capacitor back around it. Okay, going into an output stage, which we'll just say has a gain of 1. Okay, for right now. Okay. Let's think about what happens when we put this big step. Remember, this is the problem we have. Let's keep the same. Any op amp will have the same effect. It doesn't have to be this kind of feedback we have here. We put a big step in here. It's easiest to see here, though. We put a big step here, and before this output changes, right, we have the full voltage across this input. Full voltage across that input means full voltage across this. So let's say what happens here is that if we put a volt across this, and let me just look at the differential response. There's also a common mode response in this thing as well, right? So in actual fact, that's another thing to worry about. If you get very fancy op amps sometimes, much more fancy than this one, you have a common mode settling you have to worry about too, okay? And that's often another design problem that we're probably not going to have to deal. Somebody's asking, what do you do in 240? It's some of those kinds of issues that you have to begin to deal with. In fact, one of the op amps we quite often work with is a differential input and a differential output. Okay? When you have a differential output like that, we have to put in another feedback network to set the output voltage, the common mode voltage of the output, to some reasonable value. So there's another feedback network inside here called the common mode feedback. Okay? That can have a settling time associated with it. We're not going to do that in this class, but that's a 240 thing, right? That's if you have differential in, differential out. So single-ended out actually simplifies life a little bit for us. Okay. Now back to this. We're only worried now about the differential settling response of this thing. Okay. So the first thing that happens, let's say we put a volt across here. So this goes differentially. This goes up a half a volt, and this goes down a half a volt. If you remember back to our output of this circuit, the large signal output of a differential pair, what happens when you put a big differential input voltage across the input, okay, big VID, okay? What happens is when that gets, now we're talking about large signal, we put a signal that's above, sort of about 3, I think we had like, a few VD sats, right? A couple of VD sats here, right? Something like that. You're beginning to saturate out, okay? This thing begins to actually cut off, okay? What's going to happen is this side, this is going to turn on for this circuit. This side's going to turn on very hard. This one's going to turn off. So this transistor, like I show here, has 0 current coming through it. If there's 0 current coming through this transistor, okay, let's just cut that off. That means all of ISS is coming through this M1 because this is turned on really hard. Okay. If this is turned on really hard, all ISS coming through there, all of ISS will come up into this current mirror. It's then mirrored over on the other side, and then we have all of ISS coming out into this next stage. So we're basically running way out in this region way out here, half a volt's way out here. So this circuit turns into a current source. We have this big differential input. We can just replace all of this differential pair. Forget the small signal modeling for a while, because this guy's off, this guy's really on, okay? So we end up with a circuit that looks like this. ISS driving a gain stage with a capacitor around it. And this is our compensation capacitor, okay? And then to a gain of 1, okay? So this gain of 1 is not too important to us. It's really what's happening back here that we really care about, okay? This is our final V out. Well, what happens when you have a current source driving a circuit like this? What's it going to do? It's going to be a ramp, right? This is an integrator, okay? In effect, if you just think about it, you take a current source and take a capacitor, right? What happens to the voltage on this capacitor right here? You know, it just integrates this current, right? Okay. So this first period of time, this slew rate period I've been talking about, is what it is this differential pair turning into a current source, driving, and we have to make this compensation capacitor very big, typically, right, in order to make the gain, this amplifier stable. So we end up with this C sub C of this compensation capacitor, okay? So here, I analyze this. So ISS equals, if we say that there's a reasonable amount of gain here, right, this is V out minus V in, right? But V out is much, much greater than V in, so we can forget the V in here, okay? So we end up ISS equals minus C sub C times dV dt. Well, the slew rate is simply, the way we characterize that is the slope of that curve. This is V out, okay? This is time this way, and this is V out. And this is dV out dt, okay? The slope of that. Well, what's that slope going to be equal to? Well, it's going to be equal to minus ISS over C sub C. Well, this is an inverting amplifier, right? So the slope's going to be in the other direction. But forgetting about that for a second. So what happens is, okay, this is the slew rate. dV out is just simply ISS over C sub C. So the bigger you make that capacitor, the slower the slew rate. If we integrate this, we say V out equals 1 over C and integrate with respect to time, we get this as a linear function of voltage, right? So that's what we're talking about. So this is the number we care about. Slew rate equals the current divided by C sub C. So as we increase the current, we can increase the slew rate. As we increase C sub C, the compensation capacitor, to make the thing stable, we decrease the slew rate, okay? So there's a function. So now look what's, I'm going to go through a little exercise right now that's going to talk about the coupling between slew rate and compensation. Yeah, what you might.
You only care about direction. I mean, magnitude of the.
Yeah, right.
I mean, what does the gain stage do? Like, why do you even need the gain stage if you just said it was the same thing if you just drove a capacitor directly with the current source?
Why do I need this at all?
The gain stage, like under it, because you drew a picture before, just a current source going into the capacitor. Well,
in actual fact, for this it doesn't really matter, right? I mean, it's the.
So you just waste area.
Well, why do we have this C sub C here? Why do you have this gain stage? What happens in your project 1 if you needed to do a gain of 1,000, which we have to do at least a gain of 1,000, right? Can you get all the gain in one stage? No, right? As you well know, right? So that's why we have another gain stage, right? And why do we put the compensation capacitor across that second gain stage? To make C sub C small. No, slew is not good, right? We don't want slew, right? No, we put the compensation capacitor. This is just our good old common source stage, right? this is, and here's C sub C right here. So I just took the gain stage out and just put in, the common source stat and just put in gain here. Yeah.
Is there a reason you're not Millerizing that capacitance?
Well, I mean, I'm looking at the response, the DC response of this circuit, right? And I'm not trying to calculate the effective input impedance of this thing, right? I mean, I guess I could. Okay, but since we did this, this would be like A sub V times C sub C, right?
I mean, just wouldn't it look like more capacitance than just C sub C because of that gain loss?
But this is the closed loop response that I'm after here, right? I'm after. So when we open, what we did when we Millerize, okay, right, is we're trying to not take into account the effect of the feedback, right? We're trying to remove that effect and just figure out what its effect is from an input impedance standpoint. What I'm really interested here is what happens after this compensation capacitors around the feedback around this gain stage here, right? So I'm really interested in what this voltage here is, not really what's happening at this point right here. Okay. Yeah, I mean, I guess it will work out. I guess what'll happen is so here's the input error voltage we have here, right? So the input error voltage will be ISS. This is V error. This is how the input is changing, right? V out is equal to A sub V times V error, right? So the AVs will cancel out, and I'll get, on the output side, I'll see ISS over C sub C as the output voltage change. So that would work. Okay? Now, so let's get all these things together, because this is kind of confusing what I'm going to do here. What I'm going to show you is the connection between stability, bandwidth, and the slew rate problem. This is all coupled together very tightly. If you make one better, you're going to make one worse. You want to find these kinds of things, because if you don't explicitly understand what's happening, right, when you go in and try to do your design, you sit there and work like crazy on this part of the problem, and then you go back a little bit later and look, whoops, what happened over here, right? So then you go work on that a while, and you go, whoops, what happened over there, right? You sort of get yourself into a feedback loop, right? Which is not a good one, right? So I think got to find these things, and this coupling of, of slew rate and compensation is very tight. Okay, so let's try to follow me on this one, okay? It's actually a good review of the compensation stuff as well. Okay, so let's start off with compensation that we know and love, 45 degrees of phase margin, okay? So 45 degrees of phase margin means that at the second pole, we have a gain of 1. The loop gain is equal to 1, okay? Let's do this for f equal to 1. Now, these considerations change if f is different than 1, right? But that makes it easier for us. And this is the worst case compensation problem. So that means that for our loop gain will be equal to A0, the low frequency open loop gain of our basic amplifier. Okay. Now, and we need to have it get down to 1 by the second pole. So where does that mean that the first pole has to be? Since this falls off inversely with 1 over frequency, that means this guy has to be at where? If I want the gain, if I'm at this point here and the gain's A0, and I want the gain to be 1 at this point here where it's frequency omega P2, where does this frequency have to be? A0 divided by omega? Omega P2? Omega P1 equals A0 omega P2? No. What's wrong? A0 divided by omega P1 equals omega P1. No, I'm sorry. I'm sorry. Everybody's foolish because this is how can you have frequency inversely with frequency here? That's another problem right here we got, right? So, yes, close. Okay, I just long week. I know that's right. That's why I let the homework due next Monday, right? So you got the right. So, okay, mega P1 is got to be. We got to drop by a factor of A0. Okay, all right. So that it's inverse with frequency. So that means we simply have to go back from mega P2 by a factor of A0, and that's where mega P1 is. So this is, okay? Now, we'll call this the compensation pole. Let me call that omega C now. So the first pole is our compensation pole. We call our dominant pole. So dominant pole equals compensation pole equals the first pole, okay? The first non-dominant pole is the second pole, okay? So remember, keep those names straight. Right? Okay, so now we figured out where the compensation pole is, the first one. Now let's go in to look at, let's idealize or simplify this circuit so I don't have to draw everything over and over again, okay? So we have a differential pair driving this gain stage. So here's the differential pair driving this second gain stage. Okay. The gain of this differential pair is going to be equal to what? GM times the output resistance of this differential pair, R0 differential. This is from R0 here. Okay, so we have an output resistance of this differential pair times GM. This is GM of the input, GM1, okay? GM in, let's put it that, okay? Keep track of the GMs here. So the differential gain here is GM of this stage, which is, GM1 or GM2, times the output resistance of this stage, okay? That gives us the gain. Our compensation pole now is going to be what? Well, if we have the output resistance of this stage, R out differential, and times the Millerized, okay, capacitor here, which is A sub G times C sub C, right? So this is C Miller of this next stage, where A sub G is the gain of that common source stage, okay? Now, we just said a second ago that the compensation pole needs to be equal to the second pole wherever it comes from. I didn't say where the second pole came from. It can be anywhere. Maybe it's in the output stage. Maybe it has to do with the output of this gain stage. We don't care. I'm only worried right now about if there's a second pole somewhere. Okay? So we're pretty independent of where it actually has to be. I also assume it's not moving with respect to the things I'm changing right now. So that may be a little bit problematic if it happens to be to do with the output of this gain stage. But bear with me on this. Okay? So second pole, it's fixed. A0 divided by A0 gives us where our compensation pole needs to be. So I can now, and A0 is equal to the differential, the gain of this stage times the gain of the second stage. Right? So A0 equals A diff times AG. So this is the total gain of the op amp. Okay? So I'm just replacing A0 by the total gain of the op amp divided into where the second pole is. And that's equal to this. Now notice something here. What I'm going to do now is solve for some things, but look what first is happening. So omega P2 over A diff times A sub G equals, and this is where these dependencies are beginning to show up. So let me just, because I'm going to cancel something out here, and we've got to be really aware why it cancels out. Notice A sub G is over here, and it's over here. So far as this little relationship I've just worked out on the compensation, it's independent of the gain of the second stage. So why is the compensation have this? What's going on here? Omega P2 over A diff, okay. Somehow or other we got rid of this second stage here. And now let's solve for C sub C, okay? Okay, so we got omega sub P2, and let me keep going here. A diff, what is A diff equal to? Let's put that in there. I didn't do that yet. That's equal to G sub M of the input times R out differential, okay, which equals to 1 over R out differential times C sub C. Well, notice now that we expanded out what A differential really is, and we get the R out differential in there, that cancels out. So C sub C, the size of the compensation capacitor, ends up being equal to GM over the second pole. So why did the R out differential cancel out? It's because as the output resistance of this stage goes up, that gives us more gain, which causes this to move the C sub C to a lower frequency. But as R0 goes up, C sub C can be smaller because that's the time constant. It's 1 over R diff times C sub C. So the two cancel out. Similar with AG. As AG goes up, we need to have C sub C to be smaller because we have more gain we have to kill. But A sub G, the C sub C is around A sub G, so the Miller multiplication makes C sub C to appear larger. So it cancels out. Yeah.
Can you repeat the RL differential?
Repeat which part?
The RL differential.
The R where that comes from? The R out. How's that cancel out? Okay. So let's just, I'll do that. Let me just get to the answer here. So the C sub C, the compensation capacitor, is a function of GM of the input differential pair and the second pole wherever it happens to be. In other words, mega P2 is equal to 1 over C sub C times 1 over GM of the input. Okay? Now, C sub C, what sets it? What sets C sub C is we've got to reduce the, we have to make the pole of the, we have to make the low frequency pole, okay? This guy right here, we got to make this lower, right? That's we make C sub C larger. But really what we're doing, omega compensation is equal to 1 over R out differential times C sub C. So it's not just making C sub C bigger that we have to worry about. If we could somehow make R0 diff bigger, we could also make the compensation, you know, pole at a smaller frequency, right? I mean, this has to be at omega P2 over A0, right? So we're trying to make this small. We make it small by making C sub C big, or we can make it small by making R0 diff big. But making R0 diff big does what? Making R0 diff big makes the gain of this differential pair bigger, right? If I make the output resistance, let's say I cascoded this. Make this a telescopic kind of thing, right? I cascoded this. I make R0 diff really big. But then what happens? The gain of this stage, A diff, gets really big. So then I have to make, if the gain gets bigger, that means I have to make that compensation pole even lower, right? I mean, remember the compensation pole, where was it? Omega compensation equals omega P2 divided by A0, right? Which is equal to omega P2 over A diff times AG, which is the second stage. So if I make R0 diff really big to make this small, right? Then A diff gets really big. And so then I got to make it even smaller so it can't, so it doesn't have any effect. Right? Yeah.
So your omega P2 is then just your unity bandwidth frequency then?
Yes, that's right. We can see that from here, right? What do we do here? So we made the gain equal to 1, and that's at omega P2. So this is our unity gain frequency, right? Exactly. Okay. All right. So, okay. Got that? Not really. Okay, so I'll try again. But let me finish up here. Okay, so we end up with GM, a formula for G sub m of the input over omega P2. That's our compensation capacitor. Now, remember our slew rate. What's our slew rate equal to? ISS over C sub C. Okay? Let's now work with this a little bit. So let's let the slew rate, let's plug in for C sub C this formula right here. So I sub SS over GM of the input over omega P2, so I'll bring that up in the numerator, omega P2. Okay? Let's let GM sub n be equal to 2, we know what that is. That's 2 times IDS over VD sat. All right? What's IDS for this? Now we're talking about the small signal G sub m. Okay? So IDS for this circuit, all right? This circuit. Where is this circuit? ISS here, so when we're in small signal, this is ISS over 2 and this is ISS over 2, right? So this is after we're getting out of the slew rate condition. We're beginning to settle. So IDS equals ISS over 2. So I plug that into here, I get 2 times ISS over 2, well, let's put in, over VD sat. The 2's cancel. So this is equal to ISS over VD sat equals G sub m. I plug for G sub m into here. So I get rid of G sub m and I plug in ISS over VD sat. The ISS's cancel. All right. So finally, our slew rate ends up being equal to omega P2 times VD sat of the front rate, slew rate. And you're stuck. And it's because of the compensation. If you want to improve the slew rate, you think, well, geez, I'll go in and I'll improve the current. I'll increase the current. Does that have any effect? Huh? It actually does a little bit, because it makes VD sat a little bit bigger, right? But not very much, right? VD sat goes like square root of the current, right? Play around with C sub C. You know, you really get stuck here. So really, how would you make the slew rate larger? Increase the current a little bit would help. That helps very weakly. What would the other thing you could do? Yeah, slew rate. That's faster, right? Slew rate, dVdt makes it faster. I want a slew rate to be infinite.
You want a lot of slew rate.
Yeah, I want a lot of slew rate. You're right. I mean, I want it. Is this a lot of slew rate or no slew rate when it goes instantaneously?
Yeah, it's a lot.
That's a lot. Yeah, okay. That's a lot. Okay. Slew rate, I want to be infinite. Yeah, okay, you're right. I want a lot of slew rate. Okay. I want to maximize slew rate. Okay, which is right. Good point. You got me there. Okay, so I want to make VD sat and omega P2 big in order to make slew rate really big, right? So omega P2, that's the good old second pole. That's always good to get better, right? The second pole is always really what you want to have as large as you possibly can. So that helps everything in some sense, okay? Because that really what sets the bandwidth of your circuit is that second pole. Because the first pole we get rid of by making it the compensation pole, okay? The other thing you need to do is make VD sat bigger. Well, what's making VD sat bigger? Think of one way to make VD sat bigger. One way to increase current. That takes a lot of power, and one way to do it. Another way you can do it is making the W over L small. Right? That makes VD sat bigger. That seems kind of weird. right? In fact, when MOS first came out, okay, compared to bipolar, the effective VD-SAT of bipolar is smaller, right? It doesn't take much voltage across a bipolar transistor to get lots of current. People would say, wow, MOS is really good for slew rate. Why is it really good for slew rate? Because it takes a lot of voltage across it to make any current come out of it, right? That seems really bad, right? But in actual fact, it makes MOS have really high slew rates. How would you make, here's a little design problem for you now. Now that you know that what really is important, it's the voltage from here to here that I have to have large to sort of increase the slew rate. Yeah, question?
For this, like you said, it's not small signal yet, and all the transistors aren't in saturation. So, are you still saying like you're still putting that in?
You caught me. You found me out here. Okay, so this is actually another little trick I pulled on you in this little discussion here, right? I sort of switched between. Really good. You watch that. We started off calculating slew rate as being a function of nonlinear operation. So GM of this thing is all over the map there at this point in time. It's not anything what I calculated towards the end there. But when I finished up, I started beginning to do, when I did this compensation business, I'm talking about small signal settling, right? So in some sense, I took design equations from a large signal period of time, the slew rate, and those and the design equations for the small signal settling, which is this compensation capacitor calculation, and I put them together. So it's actually different points of time that I'm really working with design equations, right? And so it's relevant here, but you're right. I've been inconsistent, and it's not the same period of time when I put these two design equations together. Okay? By that. Why are you allowed to do that? Why are you allowed to do it? Because I'm worried about slew rate as being a specification. I'm worrying about the circuit being compensated as a set of specifications, right? Those two set of design equations are interrelated, okay? I'm showing you what that interrelationship is, right? Okay, so it's just kind of, if you got total, if I put area, I could have area as part of my design equation, right? It's kind of like your figure of merit issue. I'm sort of working with a figure of merit here in some sense, and I'm showing you how this figure of merit of slew rate and bandwidth, okay, are interrelated, okay? If you can find these things out, it's really good. I mean, obviously, if you do a new circuit, there'll be relationships like this. And if you can uncover those, then it just makes your design problem so much easier, as you can obviously see, right? I mean, all of a sudden, you know what's really causing. Typically in design, you work on this to make this better, something else goes bad. If you can figure out why that's true, then you're really better off. Okay. So let's finish this little baby up. So we end up. I want to say something here. How do we make this voltage larger? The voltage from here to here. How do we make VD-SAT appear bigger? Another way of saying this, G sub m times VGS is kind of that's what we're talking about here, right? And, VD-SAT is the VGS that we put in here. What we do is we like to make this VGS larger. How can we make that larger? That's a big, tough question here. Effectively, what we're trying to do is make the voltage from this gate to this point right here larger. What happens if we degenerate this? If we put a resistor here? In actual fact, reducing the G sub m of these input transistors makes the slew rate better. Okay? That's really what we're talking about here. Having a bigger VD-SAT, where did that come from? It came from the fact that GM is inversely with VD-SAT. So if I degenerate this circuit, right, I end up with GM of the input is equal to 2 IDS over VD-SAT times 1 plus GMRS, right? That's the degeneration due to the, if I put in a source resistor here. What does that do? If I degenerate that, VD-SAT times 1 plus GMRS, that stays in there, so this goes out to 1 plus GMRS. So I increase the slew rate by degenerating these two input transistors. Well, you actually, but I may keep gain, right? If I degenerate this, right? The output resistance goes up, right? So I get more gain. But I mean, I reduce the G sub m, the output resistance goes up. Those two things cancel out as we saw in the past, right? So I don't really lose gain by doing this. If I degenerate this up here as well, right? Okay. All right. So should we take a short break? That was a lot of stuff. Yeah, right. So that's my throat sore. Water.
Oh, it doesn't affect me. It always, because like, always happens. Like, the first thing you do is you increase the large signal. So basically, it's measured.
Oh, you do? Don't they show like this thing camera over here?
So it's kind of like measuring the response time of the output voltage. So how long does it take for the output voltage to get to where you want it to go? Why? Oh, because
Well,
I think it's
why did, well, now it fixed the slew rate thing. Okay.
you have like really high slew rate.
Two, okay. Why do you want unity and why?
I want it to be large as possible.
Why?
You want the output.
Because remember our small, these.
Like,
Oh,
say
good question.
you
Yeah,
have a
okay.
high frequency
I'll answer that.
circuit, right? Yeah. So
This time here, this time constant of this,
you want that to
Okay.
that thing there, is roughly 1 over the unity gain bandwidth.
Unity gain bandwidth? Why is that?
This is, if you think about a e to the minus, take this, right? That case, right?
So an RC.
RC, so let's take that there, right?
Okay.
So this is e to the minus t over RC, right?
Yeah.
And what's the bandwidth of this?
Bandwidth.
So if you say this is 5 time constants to settle, that's like 5 over, and this is the unity bandwidth, right? That's 5 over 1 over RC.
5 over 1 over RC.
Yeah, right?
Wait, 5 times RC.
So 5 times RC, like 5 time constants. I'm saying.
Okay, so you want, but wait, wouldn't that mean you want the, wouldn't that mean you want this RC to be as small as possible then? To settle faster?
Yeah.
And then
You want the RC to be as
Small as possible, which means your bandwidth.
Okay, but is that the first pole or the second pole? Because I was wondering, because you said our slew rate only depends on omega pole 2 times V
So I was like, wow, I sound retarded.
Okay.
What?
And one thing is, if you decrease
Yeah, I will.
the pole of the first one, like you push it inwards, you actually push the other poles outwards, don't you?
And my voice sounds so different.
Like, didn't you say
It
that
can.
when you...
This pole splitting thing does, yeah, right. If that's the second pole.
Like, I think my voice
After a while, that pole won't be the second pole anymore, though, right?
Oh. Okay, so you just, in general, then you want to keep all of it in as big as possible.
Yeah.
So,
This thing helps. I mean, making this big makes this output pole for here go way out. So you sort of help that one, right? So that's good.
making this big?
Making that big, yeah, right? Because you get that 1 over GM thing,
Yeah,
right?
yeah, yeah.
So you end up with another pole out here, probably, right?
Okay.
Might be a pole on the input here if this is driven by resistance.
And how does slew rate affect, you want a big slew rate, so this is small. How does slew rate affect the settling time here?
Just 2 parts. Right?
How are you?
So this is the time. This is the slew rate
Oh,
time.
you're saying right here, and then it'll start. Oh, okay, I see.
Those are good questions. I'll send them to everybody. Thanks, man. Okay, that's all. Josh had some couple of good questions here. As he always does. Okay, so let me. What's the relationship between unity gain bandwidth we're talking about and there and the small signal settling stuff? Now let me just I'll give you a sort of a intuitive argument for this. So remember, what you're going to have is there's going to be two periods of time. There's going to be the slewing period, okay? And when you get within sort of like a VD sat or so of the output, then you begin to sort of get into this small signal settling. But during this period here, you can sort of the time. This delta t for slewing is going to be equal to the voltage change. So this is let's call this delta v. So delta v divided by dv dt, right? This is the slew rate, right? Will give you the delta t for the slew rate period of time. So that's why you want to make a slew rate really fast, really big. Then, after you finish that, you go into the small signal settling. Now, I kind of said that was partially due to the, how much phase margin you had. But there's another there's another relationship here that it's complicated because once you have multiple poles in an op amp, it's not quite so clean as this. But let me give you a feeling what goes on. This is there's a decay going on here. What's the time constant of that decay is kind of obviously an issue for us, right? The time constant of that decay is inversely proportional to the unity gain bandwidth of this circuit, okay? So the small signal settling and the unity gain bandwidth are very closely related. Now, why is that? If you kind of take the whole circuit and think of it being sort of like an RC, this is with the feedback and everything, so I've kind of turned everything into just an RC, which is associated with the bandwidth of the overall amplifier, okay? In this unity gain feedback situation, this would be the unity gain bandwidth then, okay? What is the bandwidth of that? It's 1 over RC. If I put a step into this response here, okay, what does that time response to the step look like? It looks like this, right? This is kind of this period up here, what we're talking about. We're talking about the small signal settling. So this is the small signal effective circuit of my entire op amp, right? So we usually wait, at 5 time constants, 5 RC time constants, say something's settled out. So this decay here, if it's ringing, that has to do because of the stability thing. But the decay here has to do kind of with this RC time constant. This RC time constant, you can see is related to the bandwidth of this circuit, which is related in a unity gain situation to the unity gain frequency, which is 1 over RC. So you can see that we basically have here is that, if I say that this is 1 over omega u, okay, this is omega u is 1 over RC, and that's proportional to RC. So by my saying this is kind of proportional to the unity gain bandwidth, you see it sort of makes sense because the bandwidth of a RC time constant is like 1 over RC. The time for settling is like proportional to RC, and they're sort of like inversely related to each other. So making your circuit very fast, making the second pole at a very high frequency will make this time constant much quicker, right? We'll have this delay much quicker. So you get that? So this is kind of proportional, inversely proportional to the unity gain bandwidth. This is, inversely proportional to the slew rate, So you got to work on the slew rate to get this down. You got to get the unity gain bandwidth down or up in order to make this settling fast. And you got to keep the stability relatively high, or the phase margin high, so this thing doesn't ring a lot. Okay. Let me just say something to you. This would be, I don't think you can get away with this. But what happens if you only had a single stage? Think about that. If you only had a single stage, if you get all the gain in one stage, Then what happens? So let's take that case. So let's say we have a differential pair, and we get enough gain in just the differential pair, and we have our load capacitor hanging on the output of that differential pair. What's the phase margin of this circuit? One stage. 0. How much? You only have one pole here. Let's call this C load. Let's call this R diff. Mega P2 is infinity, let's say. Right? So what is the phase margin of this circuit? You get 90 degrees from this right here, and that's it. This circuit has a nice 90 degrees of phase margin. And you can't screw it up. That's pretty neat, right? And you can see that and generally we're trying to drive a load capacitance, so the compensation capacitor, but you don't really need one, but really is the load capacitor, okay? So there's no stability problem if you have one stage. And you can drive a tremendous amount of capacitance and it doesn't hurt you. You put a lot of capacitance on this circuit, or if you do this even, if I put an output stage here, let me put a ×1 output stage. I put a big load capacitor here. Now what? Now how many poles do I have? 2. I got the one from this first stage and I got this output. Now I got stability problems. So if you're driving a capacitance, what does that tell you? Don't use an output stage. It's kind of interesting. So it's a transconductance amplifier. So if you only have a pure capacitance you need to drive, stay with one stage. And that's why a lot of the circuits, the switch capacitor circuits, A to D converters, all these circuits that use capacitive feedback and capacitive loads, generally use what kind of amplifiers? Folded cascode, telescopic. They're just great, right? You have 90 degrees of phase margin, more capacitance for load, doesn't hurt you, the thing's always stable. Makes the projects really easy. That's what we did last semester. For you guys this semester, I know you'd want more of a challenge. So we're designing this in such a way that you have to have 2 stages. And basically you have a resistance out here, right? If you have a resistance out here, then you have to have an output stage, right? And then you're kind of screwed, right? Not screwed. I'd say you get the challenge of a more interesting circuit, right? Right? That helps. Okay, so let me do the other thing we need to do about your homework. This good old Miller op-amp, the one we love so well, okay, has a really fundamental problem. And when people first started doing MOS op-amps, and they took Miller op-amp, this was a very standard bipolar amplifier design. So people just took the bipolar amplifier, stuck in MOS transistors, tried to make it work, and they discovered all of a sudden you couldn't ever make it stable, right? No matter what C sub C you put in, it still was unstable. So that kind of caused some consternation for a while, okay? In fact, there was some work that went on here. Research was done here at Berkeley. And it turned out the problem is this. Remember when back a while ago, when we first did the analysis of this circuit, right? Or actually, I put a load resistor up here, right? Let me try again. When we did this circuit in the beginning, right, and we just worried about this CGD here, we found, and we have a resistor here, we found that the poles, there was a 0 for this circuit. We had a couple of poles, right? There's the pole on the input side here, right? There's a pole on the output. And there was a 0 in the right half plane at GM over CGD. Okay? Now that 0 wasn't a big problem for us because it was at a pretty high frequency. CGD is not very big. GM, not that large anyway. So this was a pretty high frequency 0 and didn't bother us too much. Can you move my head? I'll move this, right? You move my head, right? I gave you till next Monday. You should be nice to me, right? Okay, so what happens when we make this bigger? We put a big capacitor across here, right? C sub C. That makes this plus C sub C. So this 0 goes shooting in. Okay, so now, why is that a problem? So let's do our little Bode plots. Remember, this is right half plane. Where is the right half plane 0? If we look at our transfer function now, it's going to be 1 minus j omega over omega z. Omega z in the right half plane, okay, means there's a minus sign here, okay? We have 1 plus j omega over omega p for one of the poles, omega p1. Let's say 1 j omega over omega p2. These are left half plane poles. It's a plus sign, okay? If we plot the Bode plots on this thing, here's omega p1. It comes down. Here's omega p2. It starts coming down. But depending where this omega z is, what can happen? It will cancel out this second pole. Let's let omega z, if C sub c is big enough, it could actually be sitting back here. So let's put omega z right here. And what's going to happen? Our response will actually do this. It'll come down here and then flatten out until the second pole, and then it'll start off again. This 0 here actually causes the gain, that increases while the poles are decreasing, so it actually can compensate for the fall off of our compensation pole. In fact, that's another way to see if you have zeros. You look at your frequency response like this and look and start to see if you see that change of slope begin to happen. That means you got a 0 you're having to deal with, what you have to really worry about. Okay? So this is a big problem, right? You can see what happens if I increase C sub c, because omega z is equal to gm over C sub c. As I make C sub c larger to try to bring this pole back further, what happens? This 0 goes back further. Right? So I move the C sub c larger, I do this, and I just do this. So if this thing was unstable to start with, by increasing C sub c, it doesn't help. You can make it so it cannot be made stable. Okay? So it's a right half plane. Yeah.
Actually, I'm not quite seeing why this circuit is not stable. Because if you make the kind of if you shift the first pole to the left,
Yeah.
and then it seems like increasing your
But how are we moving it to the left? We're moving it to the left. Mega compensation pole is equal to 1 over R out diff, right, times C sub c, right? So we're making C sub c larger, which moves that 0 over, so it just compensates. So it doesn't help us to move that lower frequency. Okay. Okay. So what do we do about it? Well, there's several things you can do. The problem is, the real problem we have here in this circuit, it's the feed forward through this. I mean, this is inverting, right? So we put in V in here. This point here is minus A times V in. It's the fact that this signal, when it feeds forward through this capacitor to this inverting side here, and it cancels out that side there, is what's causing this 0. So what I can do is I can put a circuit here that doesn't allow this to feed forward and sum into that node. A circuit like this will do it, right? I put a source follower here that comes from our output, and so we can't feed forward through the compensation capacitor because it sees this source follower. So this has only a signal in this direction, very weak signal in the forward direction. So this will kill the 0 just completely. There's no problem. It's just gone. Right? There's no feed forward through here. And your problem with this circuit, though, is you got this extra source follower you have to deal with, right? And current associated with that. So actually, with some students from here that actually figured out that you can put in a little, simply adding a little resistor in series with that capacitor, and you solve the small signal expression. Now you got to solve the and forget this, ignore for now. I don't know why I was there. This is the whole problem. You put this little RZ in here, and you resolve where the 0 is. The poles don't move very much because this RZ is relatively small. And you end up with a 0 here. Before it was at G sub M over C sub C. But after you put in that RZ, the series resistor with this capacitor, in other words, you just in this circuit right here, I'm sticking a resistor right there in series with the C sub C. Here's where the new 0 location is. It's 1 over G sub M minus, and this is G sub M of this transistor right here, this common source, minus RZ. So as RZ gets larger and larger, it's its opposite polarity from where the 0 was before. It puts the 0 into the left half plane. So when RZ is much, much greater than 1 over GM, then this goes to R1 over RZ times C sub C. It's minus that. If you want to put the 0 at infinity, and that was your homework problem, what you can do is you can just set 1 over GM equal to RZ. And let me get the last thing to say about your homework problem is when we do this, in your homework, the way we did it was we put a transistor in there, right, in series with your, right, and this is current source. So this is the RZ. This is going to have a very small voltage across it, okay? So this is actually in linear region operation. So remember we talked about we rarely put things into linear region operation, but here's an example where we do. We're trying to make this transistor, look like a resistor. And fortunately, because it's a transistor that's like this transistor down here, it's not that difficult to make this look like a GM, 1 over GM, and have it match the 1 over GM of this transistor down here. And when we do that, then this 0 goes to infinity. Right? The GM of the 1 over RD, remember, just want to do one last thing for you. If we have a transistor like this, and let's say I have a VDS here across this transistor, let's ground this. What's the resistance looking into here? Okay?